a little bit of a peripheral topic. But we talked about how in depth about how RISC-V is designed, how it's done, and why some of these decisions that they made were good. That's one end of the spectrum, because RISC-V, like I mentioned before, RISC-V has the benefit of hindsight. It has the benefit of knowing what worked over the multiple decades of doing CPU design and what didn't work. So they could afford, and of course, it's still, a lot of people are still debating a lot of things, but at least at a meta level, they were able to take advantage of data-driven designs and the things that they know have worked or have not worked. So a lot of these design decisions that we talked about are kind of data-driven, are kind of based on, hindsight is 2020 kind of benefits. On the absolute other end of the spectrum is x86. And x86, as we talked about before, is a more of a, if you're familiar with this term, it's more of a bizarre kind of a design. There was a software engineering book that was popular a couple of years back talking about cathedral design and bizarre design. Cathedral design where someone actually designs the things from ground up, as opposed to the bizarre design where things kind of organically just grow. And x86 was definitely on the side of the bizarre type of design. And looking at this history and looking at some of the pitfalls, some of the strengths that they've had is also kind of interesting to give a fuller sense of computer architecture development. So let's go into that for a little bit before we move on to circuits. So history. The history of x86 can probably be described in one sentence saying evolution with backwards compatibility, because they religiously, well, at least as an end result, they have religiously maintained backwards compatibility. So in the beginning of the world, there was a couple more processors that Intel has built before the 8080, for example, the 4004 processor. But in terms of the legacy of x86, it all kind of began with the 8080 processor back in 1974. It was an 8-bit microprocessor. It didn't have many registers. It had an accumulator, which is pretty much another word for just a register, one register. And 8080 was widely successful. It was used as the basis for a lot of IBM PCs, and it spawned many clones that shared the same ISA that was pretty much binary compatible with the 8080 processor. And 8080 was a fairly simple processor, looking at it from our current knowledge. If we wanted to do a hardware design lab for the 8080 and we knew exactly what we're implementing, it would be a fairly simple thing to do even at the undergrad level. So after the end of this this course, if you're looking for an interesting summer project, maybe that's something for you. But anyways, the 8080 was widely successful. It was a very successful chip. And one of the clones that was built by this new company at the time, Zilog, which were founded by a bunch of former Intel employees, incidentally, created this expanded backwards compatibility version of the Intel 8080 called the Zilog Z80. And it is absolutely still manufactured today. It's used in a lot of embedded systems. It's all over the place. And I mentioned Game Boys a couple of slides back, and actually the original Nintendo Game Boy used a pair of, not quite Zilog, but something built on top of Zilog's, because of course, it being a game console, it required things like sprite management, these special functions for port map video processing. So, but it was absolutely based on the 8080 and the Zilog Z80 chips. And Game Boy used two of these. A lot of Pac-Man used, the original Pac-Man game console was built on the Z80, I think. And a lot of arcade game machines at the time were built on top of Z80s. And the operating systems that were written for it, well, ported for it, CPM, all these things are still around. They're used in all these little nooks and crannies. It just shows how immensely popular this chip was at the time. So this was kind of the breakout point for Intel. It became a really successful manufacturer. And the 8080 was an 8-bit microprocessor, and its limitations were pretty obvious. 16-bit address buses, it's not particularly extensible or future-proof. So based on the success of the 8080, Intel at the time decided the next one's going to be future-proof. It's going to be a really, really good processor. It's going to be a well-designed from ground up based on the knowledge that we have, so on and so on. So they announced what is called the Intel IAPX 432. I have no idea what these numbers are actually supposed to represent, but it is the first 32-bit architecture CPU that Intel designed. It designed a new ISA, not backwards compatible to the 8080, but I guess that didn't mean too much at the time because they only had 8080, only one processor to be or not be backwards compatible to. And it had a lot of academic features, a lot of high-level language features built into the actual silicon of the chip. It had a memory access controller, which would not come into mainstream Intel chips until a decade later. It had garbage collection support. It had lots of things, data structure support in the hardware built into silicon. Because I guess at the time, we didn't have too much experience. Well, I say we, just designers in general, didn't have too much experience in terms of the balance between what to put in software and what to put in hardware. A lot of experiences were coming from the people who were building supercomputers, and supercomputers had a lot of chip space and lots of chips in general to do these kind of things to speed up execution and so on and so on. So that kind of expertise was being brought into this chip design. Interesting thing is it wanted to become as high-level language friendly as possible. So funny thing is it did not have explicitly addressable registers, no X0s to X31s, no anything. It had no explicitly addressable registers. It had a stack and a memory space, and I guess it kind of partially answers the question that I posed to in a couple of slides back about why 32 registers, why not 1000, why not 0? And this was a tentative answer to that question given at the time. What if we didn't have any registers? And just, yeah. There were, of course, registers, but it was supposed to be maintained by the compiler, maintained by the architecture. The assembly code was not supposed to be able to see it or edit it in any explicit way. And funny thing is, it was a bit-aligned variable length ISA. And this is kind of insane when we look back at it, because RISC-V right now are 4-byte aligned. So all instructions are located on, 4 bytes from each other. But the 432 was supposed to have variable length instructions, not in the granularity of bytes. It had a variable length instruction set in the granularity of bits, pretty much saying it was not aligned at all. So so each instruction was wildly different in terms of length, in the units of singular bits, meaning when you decode an instruction, when you read an instructions, you may have to read the next instruction 7 bits away from it, for example, which complicates logic quite a bit. And the thing was, based on the fabrication technologies they had at the time, this circuit was way too large to fit in any kind of a package that they were able to build at the time. So the 432 chip was spread across 2 separate chips, and their communication between, so one had decoding and the other, because you can probably imagine decoding with like reading and making sense of the instructions and, making sense of the variable length instructions, all that stuff, was big enough to fill up a chip. And the other chip did the actual computation. The problem here was because the chips were communicating over the motherboard, the communication speed was kind of dictated by the signal speed that you could maintain over the motherboard, the copper cables on the motherboard. And we'll get into that in the very next lecture. It's very, very difficult to maintain high performance, high speed signals over long copper cables, long meaning in the order of centimeters. So the bottom line was that the 432 was a very expensive and very slow chip, which was, I listed 1975 here because that's when they started development, but it actually came out multiple years later. So when it came out, it was an expensive chip, it was a slow chip, and yeah, people didn't really care about it too much. So that was the first big downside, the mistake that Intel made. Although people do argue that the 432 wasn't necessarily a big mistake that they made. It was kind of a learning experience for Intel. So anyways, on this right, you see these are actually CPUs, the original Intel 8080 chip, the Zilog C80 chip, which was a kind of a clone of the 8080 chips. And one of the many, many clones, it's a Toshiba clone of the 8080 as well. This is from a point in time when CPUs had small enough number of pins going to the motherboard that we could build it in a DIP form factor. So the 432 was a big mistake from big learning experience for Intel. And even before the 432 actually came out, it was becoming fairly obvious that it was not going to meet the timing, meet the release time that Intel required for it to, take over the world. And especially since other chips, at this point in time, Intel wasn't the only biggest player in the area. Motorola were building really nice chips that Macs were being built on top of. Of course, the Z80 was pretty much eating their pie. So Intel had to move very quickly to retain its customers. That's when the Intel 8086 chip was designed. It is a 16-bit extension to the 8080. It was intended as a temporary substitute until the delayed IAPX 432 became available. I think at this point, Intel still had the hope that if the 432 chip came out, it's going to take over the world. And the 8086 was supposed to just act as a stopgap to retain customers until this new fabulous chip came out. So the rumor has it only took something like a team of 3-4 engineers like a week to design the 8086, and people sometimes point and laugh at it saying, oh, that's why the Intel x86 ISA is so dirty. But anyways, it was backwards compatible with the 8080. It was a CISC instruction set because, they wanted to be backwards compatible while extending the instruction set. And the 8086 was also a massive hit. I guess also partially riding on the coattails of the 8080 chip as well. Later, they also introduced the 8087 chip, which you see the photo here on the right. It is a floating point accelerator card, kind of. If you have a special slot for the 8087 chip on your motherboard, you can plug that chip in and get hardware implementation of floating point operations, which were not a standard issue at the time. And after that came here we start to be pretty much backwards compatible legacy of x86, because 8086, where the x86 name comes from, was a success. And the 8286 chip, which added support for larger memory spaces like 24-bit addresses using segmented memory, some form of protection, things like that, to the 8086 chip, became one of the staples of desktop PC hardware. This was the machine architecture that MS-DOS kind of expected. And because it was built on top of the existing technology Intel had when they were designing the 8080 and the 8086 chip, so the 432 chip became available around similar time frame as the 286 chip. And the 286 chip was a lot cheaper, and the benchmark showed something like 4 times the performance of the 432 chip. So I guess the 432 chip was pretty much doomed from the start. An interesting thing here, and we see one of the many dedications to backwards compatibility here, is that when the 24-bit address spaces came out with segmentation support, we will probably get into, if we have time, we'll talk a little bit about segmentation, but we will, for now, I'm just going to give a very high-level introduction saying when each task or process in the 286 chip had a choice of using 16-bit addresses as before, as this did 8086 had. And if the operating system set what is called a segment register for each process on the actual physical memory, that 16 bits worth of memory space can be located anywhere inside a 24-bit range. So from the point of view of each task or process, it was as if it just had a normal expected from 8086 kind of 16-bit address space, its own 16-bit address space, nothing else interfering with it. And this allowed very simple compatibility with legacy programs like operating system CPM and things like that, which let IBM and Intel computers at the time take advantage of existing code bases without having to ask them to write, at least significantly rewrite any of the code. That's why the MMU of the 286 chose this. If you look into segmentation in detail, and I suggest if you're interested, it's a really weird system to be implementing, but it served its goal of supporting backwards compatibility. And this decision, among many others, allowed Intel to continue retaining the customers, continue retaining the software to, continue their allegiance to Intel starting from the 8080 days all the way up to at least right now. And increasingly made it more difficult for, I guess, new players to jump into the market, because big companies, when they have a suite of software already written, they don't really want to explore outside into new and exciting architectures readily. And this continues. One of the big stories from one of the big events in terms of Intel CPU history was the introduction of 8386. It was a 32-bit extension to the previous line of CPUs. Now the extension is called IA32, and this is the target that most compilers, if we compile to 32-bit x86, this is the ISA that we target. It introduced many additional addressing modes and operations, paged memory, which is a much more saner way of implementing memory management. We may get into, it's not important right now, on top of segments. And the beautiful thing about x86 that was two sides of the coin, could be beautiful, it could be super duper dirty. It introduced what is called the virtual 8086 mode, because at this point, the ISA of 8086 and 386 had diverged quite a bit. A lot of things were built on top of that. So since the 8086 had hardware support for different processes, it allowed a way to set a special operation mode inside architecturally for a particular task or a process. And it was a simple hardware virtualization support for legacy software, so that if a process is set to go into the virtual 8086 mode, it's like virtualization, which we'll talk about in later parts of this course. From the point of view of, say, MS-DOS running in virtual 8086 mode, as far as it's concerned, there was no 8386 processor on top of it. It's running in its own 16-bit memory space with its own exclusive access to memory and systems, which meant multiple instances of DOS programs. And DOS programs at the time were very, very important, because it included things like spreadsheet programs. It included things like, well, pretty much spreadsheet programs at the time. That was one of the big things in computer usage at the time. But it could host multiple instances of these programs, video games, whatnot, to run in parallel inside a host operating system. And it's kind of difficult to imagine how big a deal that was now, but that meant that the operating system could finally move beyond MS-DOS. Prior to the introduction of the Intel 386, a lot of people tried to do GUIs, a lot of people tried to do better operating systems than MS-DOS. MS-DOS, when you execute a program in MS-DOS, it's pretty much just relinquishes exclusive system control to the software and hopes that it returns it in a nice state. But if people try to build a better operating system that does better resource management, but it was a lot of people did do better operating system development, but its reception was typically not very good, because that if you jump to this new operating system, it pretty much used to mean that you're just throwing away all of the existing MS-DOS software. But since Intel introduced this virtual 8086 mode, people could finally build operating systems that had exclusive control of the system and just kind of hosted different MS-DOS software, which they thought was having exclusive access to the system, but also encapsulated inside virtual machine support. So yeah, and Windows 3.1 was the breakout success that happened at this time. I actually posted a link on the course website about this series of blog posts called Doing Windows. And when you have some time on your hands and bored, you want to read about computer history, I highly, highly recommend reading that series. There's something like 6 posts. And one of the posts talk about how the introduction of new architectural features in this particular processor and how Microsoft did use it to do things that other people couldn't. It's a very fascinating read. Anyways, so things were good at the time. And Intel was pretty much taking over the world. And after that, there was just a series of and lots of single thread performance evolution. 486 was introduced in almost the 90s. It was the first pipeline processor. What pipelining is going to be a very important topic in this course later in a couple of slides. It had on-chip caches first introduced, FPU, the floating point operations incorporated into the CPU because we had more silicon, thanks to Moore's law. Competitors started appearing, AMD and Cyrix and whatnot. After that, the venerable Pentium CPU first was introduced. It had an infamous bug in the floating point divider module, a relic of history now. After that, Pentium Pro, Pentium 2, Pentium 3, Pentium 4. And this was kind of for some, happy days of computer architecture. Just CPUs kept getting faster. We started with something like 30 megahertz back in the 486 days. By the time we reached Pentium 4, we were reaching 2-3 gigahertz, and people were happy, except I guess some computer architects. So one interesting thing here is that you see a Pentium 2 processor, which was at the time in a card form factor instead of the plug-in chips that we are used to right now. So that's kind of interesting. Anyways, so things were kind of good. And I guess when things are good for too long of a time, that's when people start thinking about doing new and exciting things, which sometimes work out and sometimes don't. So we talked about the 432 chip, which tried to break away from backwards compatibility and wasn't particularly a success. And at about this time, Intel was running into the end of Dennard scaling, as we talked about. Single thread performance wasn't increasing particularly fast. Well, at least it was expected to. And it was time to go beyond 32 bits and its 4 gigabyte memory address limitation, because 32 bits can only express up to 4 gigabytes. It was also time to go beyond 8080 backwards compatibility from the point of view of some Intel engineers. And it was time to go beyond, with pipelining and all these things, they were reaching a regular cycles per instruction. And we talked about cycles per instruction a couple of lectures ago. They have hit a wall of 1 cycles per instructions. And at the time, it wasn't clear how you would move beyond 1. So time to go beyond all of these things was Intel's thought at the time. So they came up with this new ISA, not backwards compatible to x86, called EPIC, Explicitly Parallel Instruction Computing, the Itanium line of processors, which they called IA64 ISA, as opposed to IA32 ISA, which the x386 processors brought about. So they implemented the idea of VLIW, very long instruction word. And it's an idea that has been around for a long time. It's still around. Some people still try to see if they can do cool things with it, with some success. But we won't go into detail about VLIW because this is a topic that's typically covered in graduate computer architecture. But the point was, the bottom line was that in the EPIC ISA, each instruction, which so far have encoded one thing to do, now each instruction was called a bundle, and each bundle consisted of 3 sub-instructions. And these 3 instructions were issued at once. And if we're lucky, and if we didn't have data dependencies between, of course, if you had data dependencies between sub-instructions in a bundle, the ISA specs would not allow it. But so if you're lucky and we managed to pack 3 tasks in a bundle, we would be getting CPI of 1/3 if we're lucky, so 3 times better. So that was supposed to be the big thing. And there was lots of tricks that were played inside the ISA, lots of tricks that were played inside the architecture, the microarchitecture, to deal with data dependencies, to try to get a consistent 1/3 if at all possible. And a lot of things that were not helpful to Intel were happening at the time. It was a very complicated design to do, and they were starting from scratch, kind of free from, for better or for worse, from the all of the IP that they have created before, Pentium 4 designs, like 8086 designs. They were breaking free of all of that. They were starting from scratch. And Itanium was delayed many, many times. It was delayed a lot. And because of these restrictions, tricks were being played to manage data dependencies within bundles, the simple fact that they do have bundles at all. So writing compilers were really, really hard for this as well. So they weren't getting as good a performance as they were hoping they would get. So around 1999, when the Itanium project first started, the expected sales for Itanium were pretty good. But as it was delayed, the actual sales that happened was the orange line that you see on the bottom. It didn't really sell very much. And Itanium was supposed to be the next big thing for Intel. They invested a lot of efforts into it, lots of money, lots of everything. Kind of like the 432, I guess. And the bottom line was that it was pretty much a failure. Meanwhile, AMD was becoming a viable competitor to x86. They had good fab technologies at the time. They had good design teams. They were doing pretty well. While Intel was spending effort designing the EPIC architecture, AMD did a backwards compatible expansion of x86 to 64 bits. They called AMD 64. And later, Intel also, after they kind of decided Itanium wasn't going to be sustainable, they also adopted this extension in a bit compatible way. And it's as a result, the AMD 64 is also called x86 64. Yeah, and I guess from the point of view of Intel, I'm guessing their pride was hurt a little bit because they had to use an ISA defined by a competitor for a change. But at the time, there was really no choice because AMD had, I guess, jumped the shark, so to speak, coming up with a new ISA already. People had adopted this already, and it wasn't going to help the market if 2 of them came up with different encodings. So, yeah. And that happened. That was an interesting point in development history. And then around the year 2006, because we didn't get to go to VLIW and Dennard scaling ended, if you remember, around 2006, the Intel Core architecture came out and they went dual core. Added SSE instructions, which were kind of a remnant of VLIW cores. We won't talk about that in very much detail. AMD also tried to go beat the gun and introduce its own SSE 5 instruction sets, but Intel declined to follow and came up with AVX. And this back and forth has been going on since then. And now we're entering a new era of development, which we'll probably have written in bullets after this when we're done. So if Intel did not extend its ISA with compatibility, backwards compatibility. Its competitors absolutely would, as did, I guess, Dialog C80, I guess did AMD 64. So that's one of the big reasons that it's a blessing and a curse from the point of view of Intel, because too many people are already entrenched in x86. So that's kind of the reason technical elegance did not necessarily correspond to market success. There were arguably better designed chips out there. It's just that they didn't succeed like Intel did. They didn't have, some people say that the MS-DOS was the big breakout point, Windows, but it was a perfect storm for all of these things to happen. Oh, we're almost running out of time, so I'll jump through a couple of slides really quickly. So for those of you who are not familiar with Intel registers, Intel programming model, Intel's x86 has a much smaller number of registers compared to RISC-V. It only has 4 general purpose registers. The AX, BX, CX, and DX registers, which were 16 bits at the beginning of the world when they first developed 8086. But as we went to 32 bits, they were expanded to 32-bit registers, EAX, EBX, ECX, EDX. But the interesting thing here is if you have older assembly code, older binary, which references these AX, BX, and CXs, they're still accessible because they want to be absolutely backwards compatible. There would just be sub-bits from the extended registers. Now we also have 64-bit extensions with the R prefix, so it's RAX, RBX, and whatnot. As an aside, at this point, after a lot of research went into all of these topics in terms of computer architectural design, now we know that 4 is kind of a small number to have for registers. Intel plays a lot of tricks to get around this problem while still maintaining this program abstraction, which probably won't have time to get into this in undergrad computer architecture, but they do their best. They also have special registers for stack management, the stack pointer and the base pointer, which RISC-V doesn't have. I mean, there's only general purpose registers that you have conventions recommending that you use it that way, but not like Intel. Intel also, x86 also has a very symmetrical and expanded addressing, a bunch of addressing modes. If you remember, the load and store operations in RISC-V only allow loading, for example, loads only load from memory to registers, and stores only allow stores from register to memory. But x86 instructions typically have a lot of different addressing modes. The source and destination operands can either be from register or memory. The second source operate, so x86 assembly only typically has 2 operands. The first source operand is also the destination operand. So only 2 operands to encode inside the instruction encoding. The second source operand can either be a register or an immediate or a memory. And there's typically most combinations of these combinations. So if you do have an add instruction, you can add between 2 registers, you can add between 2 memories, you can add between memory and register, you can add between a memory and register and write it back to memory, so on and so on. It's complicated. There's a lot of debate whether this is a good idea or not, but this is what they did. And we also talked about already that x86 has variable length encoding. Yeah, but we talked about all of this, so we're not going to go into too much detail in the interest of time. And for x86, instruction accumulation has been pretty severe because we always wanted backwards compatibility. So the existing instruction set doesn't change. And every time new functionality comes in, you just add more instructions. And that's one of the big reasons that the encoding structure is not as clean as RISC-V is as well, because as you run out of bit spaces, run out of the bit budgets to encode these new flags, new opcodes, new everything, you start putting things in just random places that you don't have encodings for yet, which really makes the decoding, making sense of the encoded instructions very, very complicated for Intel processors. As of apparently 2012, the size of the number of instructions hit almost 1,000. I think at this point we have something like 2,000 instructions in the full x86 instruction set. So that's a lot compared to something like a few dozen for RISC-V. So anyways, Wrapping up the ISA module of the course, the TLDR so far has been that the design principles simplicity favors regularity. That's why RISC-V was designed that way. Smaller is oftentimes faster because you can make it go faster. And good design often demands good compromises based on data, based on benchmarks. And a big goal of that was to make the common case fast. And this theme will come up repeatedly as we go into more computer architectural topics. And the caveat from there is that having more singular powerful instructions doesn't necessarily result in powerful performance. Fewer instructions may be required, but complex instructions are harder to implement inside the architecture, which may slow down other instructions as well, including the simpler ones. And at this point in time, compared to where we were at the 80s, for example, research into compilers have progressed so much that compilers have become very good at making fast code from a set of very simple instructions. Yay, that's it. I'm sorry for running over time a little bit already. Story time was a bit longer than I anticipated, but hopefully this was interesting glance into history and why our computers at this point look like the way they do. Yeah, since we have all of this background set up in our minds, starting from the next lecture, we'll go into my favorite part of this course, talking about circuits, talking about electrical signals and speed of light, and how the residual information from the Big Bang is affecting how our processors operate, and how that kind of dictates how we design our processors.